time, let's try it together. So the diameter is 6 centimeter, which means the radius is 3 centimeter. And in terms of standard units, it's equivalent to 0.3 meters. This is a uniform diameter because the uniformity affects the way of loading. What's that? 0.03 meters, sorry. 0.03, thanks. So it becomes 30 centimeter long after the whole body is applied on it. So this is the final length. So LF is 30 centimeter, which is 0.3 meters. And we have the weight. Weight is equivalent to 80 kg. We are interested on the force quantity, right? So how do you calculate the force? The force component is, this is the mass. The force component is the weight. So we can calculate the weight as mass times gravity, right? So there is no any additional force. The force is just the weight of the body. So the weight of the body is applied on this stainless steel material. So the force will be the weight, and the kind of loading will be compressive, right? Because the whole weight is applied on this material. So this is mass times gravity, 80 kg times 9.8 meter per second square, and the unit will be in newtons because it's force. So what else do we have? The Young's modulus. It is 200 gigapascals, and in standard units it is equivalent to 200 times 10 to the power of 9 pascals. What else do we have? Nothing. So what is required? The original length. What was the original length? So we can start from this. Young's modulus is equivalent to a stress over a strain, and stress is equivalent to force over area. Area is pi r squared, and strain is equivalent to change in length over the original length. So this is equivalent to, we can calculate the area by using the radius. So we can assume it is done. So force is mass times gravity, or we already know it. Force over area divided by what's change in length. Original length minus final length divided by the final length. This is compressive force. So you have to worry about the change in length only. Divided by the original length, sorry. So if it was, so this is equivalent to force over area times L naught minus LF, right? So what is unknown from this? L naught. Only this one is unknown. So we have to take this out from the known values and express it in terms of known values. So this is equivalent to Y force times L naught divided by A L naught minus LF. If you cross multiply this, you will have Y A L naught minus this Y A LF. This will be F L naught. So collect the same terms together, which is Y L naught and F L naught. So this will be Y A L naught. If you bring this to this side, it will be minus F L naught, which is equivalent to Y A L F. So the unknown terms L naught, right? So L naught YA minus F, and it will be YA LF. So L naught will be YA LF YA minus F. So all these right side components are known. Y is known, which is 200 times 10 raised to 9 Pascal. Area is known. You can calculate by pi times r squared. Final length is known, which is 0.3 meters. So this will be around, by using calculators, the original length will be around 30.02 centimeters. There is a small difference because the weight is very small and it will not affect the length that much. You don't have change in length, you have only the final length. Yeah, that is the final length, right? It becomes 30 centimeter after the whole body is applied on it. So that's the final length. In this case, it is compressive force. So the length should be positive, right? It shouldn't be negative value. It should be positive value. We are interested on the change only. Yeah. Okay, let's continue. Bone is a viscoelastic material. It has both viscosity property and elasticity property. Viscosity is a measure of resistance to gradual deformation by shear stress or tensile stress. And elasticity is the ability to return to the original position after the load is taken. So bone is viscoelastic, meaning mechanical properties such as the stiffness changes as the strain rate changes. So we can say stiffness or strength of a bone increases for higher strain rate. Higher strain rate means higher deformation rate. So if we compare two curves, two strain stress curves, I will post the solution on Bula. So I will post this on Bula. You can find it on Bula. So we said bone is viscoelastic, which means the stiffness increases for higher strain rates, which means the strain is dependent on the stiffness is dependent on the strain rate. So load, let's say load in deformation curve, and we say the deformation is proportional to the load applied for a couple of periods. So we can have two curves, for example, depending on the strain rate. Let's say one curve, or this one is 0.02 second strain rate. That means it is the rate of deformation. You can slowly deform a material and you can quickly deform a material. So let's say this one is a quickly deformed material and the other is slowly deformed material. 200 seconds. So the deformation on this case is slow. So if you compare load and deformation, you will get this kind of curve. So the curve for quickly deformed material will be higher than slow deformed material, comparing load and deformation. So let's take one load and stretch to these points. So this is low deformation, and this is higher deformation, right? This is the deformation axis. So this is low deformation, this is high deformation. But we have same kind of load. This is one load. So for the same load, we can deform the material highly if the deformation rate is low. But if you quickly deform it, the material will resist the load because it will rearrange itself quickly, and it can resist the deformation if the deformation rate is quick. That's why a bone or a muscle or a body can withstand deformation during running, because the deformation rate is dependent on, the stiffness is dependent on the deformation rate. For higher deformation rates, it can withstand the load because it will quickly rearrange its internal structure because of this viscoelastic property. The viscosity is a measure of, or the resistance of deformation, and elasticity is the ability to return to the original position after the load is taken. So since load is viscoelastic, bone is viscoelastic, deformation or stiffness is proportional to the strain rate.
You said the bone withstands deformation.
What's that?
The bone withstands deformation.
Can withstand. It can withstand for higher deformation rate. Higher deformation rate, yeah. So the value that determines the strength of bones is called the ultimate strength. Sometimes it's called ultimate tensile strength. So the ultimate tensile strength, or the maximum strength that the bone can withstand a load, is called ultimate strength, and it is proportional to the square of density and the strain rate. So two factors affect the ultimate tensile strength of a bone. One is the density, and the other is the strain rate. So the density highly affects the ultimate strength. Higher dense material or higher dense bone have high ultimate strength. Or ultimate strength is the highest point where the bone can withstand any kind of load. So if you compare, if you take load deformation curve, you can have this kind of curve. For a couple of ranges, the load and deformation are linear up to some point, which is called the yielding point. And this region is called elastic deformation region, or we call it elastic region. In this elastic region, the bone can return to its original position after the load is taken. If you apply a load to a bone, and the bone will be deformed for a couple of centimeters, and if you take that load, the bone will return to the original position if the amount of load is in this elastic region. After this point, after this yielding point, it will enter to the plastic region. In the plastic region, the bone will not return to the original position. It will stay on that range. If you deform a bone above this yielding point, the bone will stay at that deformed region, and that is the plastic region. And the point of fracture, this P, is the final point where the bone no longer withstand a load. So after this point, fracture will occur. So this is the highest point where the bone can't withstand any kind of load. So this is a very important curve, the strain stress curve. It has two regions, the elastic region and the plastic region. In the elastic region, the bone can return to the original position if the load is taken. In the plastic region, the bone will not return to the original position even if the load is taken. And the point where maximum load is applied is called the point of fracture. And at that point, fracture will occur on the bone. That is the maximum load point. And that is the ultimate strength. That is the ultimate strength, which is equivalent to 68 times the strain rate. dE divided by dt means strain rate. Change in a strain divided by change in time. It means change in strain or change in time. This is the strain rate. And this is the density. P square is the density. Or we call it rho. Rho square is the density. So this is the ultimate tensile strength, which is the point of fracture, or the maximum load. The maximum load. And it is proportional to density, highly, and less proportional to the strain rate. What's that? This one. This is the ultimate tensile strength. This is the maximum load for a bone. After this point, the bone can't withstand any kind of load, and this is equivalent to 68 times the strain rate. The strain rate means change in strain divided by change in time, and this is the density. Change in strain divided by change in time, the power of 0.06 times density square. So we can say ultimate tensile strength is highly proportional to density because it is P square, right? And it is less proportional to the strain rate. But it is still proportional to or dependent on a strain rate. So this is the final or the highest strength that the bone could have. So according to this, according to the load, bone may fracture or break in different kinds of mode. So the mode of loading or the mode of force application determines the type of fracture. The loading and the magnitude of the force determines the kind of fracture. For example, bending with low energy may result transverse kind of fracture. This is a transverse kind of fracture. Bending with low energy. Compression plus bending plus torsion with moderate energy may result oblique kind of fracture. Torsion with low energy may result a spiral kind of fracture. Compression plus bending with moderate energy may result oblique transverse or butterfly kind of fracture. And a combination of mode of loading with high energy may result a committed kind of fracture or different kind of fracture. So the mode of loading and the magnitude of the force determines the kind of fracture. And that magnitude where the fracture occurs is called the ultimate tensile strength. That is the point of fracture, or the maximum point that the bone can't withstand any kind of loading. That is a change in strain divided by change in. Yeah, it is change in strain divided by change in time is the power of 0.06, right? This is less value than 2. So we can say this is this one is highly proportional than this one because the power, this is 0.06, right? Okay, that will be enough for today. We will continue tomorrow with the rest. Yeah, because the value. Hi. Yeah, I will post some of the examples from Bula so you can find on Bula.
I'm sorry.
Oh. Do you need the mic?
My voice is usually loud enough, but
So,
yeah, no, I can